All right. Okay. Here's what we're going to do. Today we are moving into chapter 4. Okay? We just finished up chapter 3. We're going to do some of the homework assignments, or some of the homework problems from chapter 3, which I think after doing several of them, you're going to be very comfortable with the derivative of e to the x and the derivative of natural log of x. After we do a bunch of those, we are then going to, we are then going to move on to chapter 4 and talk about extreme values. One of the primary applications of derivatives is being able to identify maximum values and minimum values. Okay? So we're going to start with doing some of the homework from section 3.9. So let's start off with something easy. Let's say that y is equal to 2e to the x. We want to know what dy dx is. What do we think? No. Well, you might think product rule because there's multiplication going on there, but remember, product rule is only applicable when it's a variable function times a variable function. This 2 is not variable. Therefore, it is a it's a constant. And remember, constant multipliers are not, we set them aside. They're a part of the derivative at the very end. So you can ignore the 2 for a minute, do the derivative of everything else, and then multiply by 2, which is the same thing. So the derivative of 2e to the x is 2e to the x. Yes. Okay. Yeah, because the derivative of e to the x is e to the x, and then we just multiply it by the constant multiplier 2. Okay. All right. Now let's try another one. How about e to the 2x? All right. So what do we got going on here? First of all, the first thing you should do when you're doing a derivative is think about what rules are being applied. Now, it is obvious we are going to apply the rule of exponential functions. Okay? But are there any other rules that we're going to have to apply? Yeah. This is e to the power. Normally, we have e to the power of x. But this is e to the power of something other than just x. And isn't that one of the ways that I told you can identify what? What rule? No, not product rule. The chain rule. The chain rule is anytime you have a function and where you would normally just have an x, you have something other than just x. So instead of e to the x, we have e to the 2x. This is a chain rule problem. Okay? 2 is the derivative of the inside, and then e is the derivative of the outside to the power of 2x, because the inside has to remain unchanged. So it's 2e to the 2x. Okay? All right. Number 3 here is e to the negative x. This is a pretty popular one. E to the negative x.
You still got to do it.
Yeah. Negative e to the negative x. There you go. Because the derivative of the inside is negative 1. Negative 1 times the derivative of the outside, which is e to the power of its function, and the inside function is negative x. So negative e to the negative x.
Do you want us to put it like 1 over e,
Oh, no. We generally, although I have done that on some of the problems in the homework, generally speaking, when you have e to the negative x, you leave it as e to the negative x. E to the negative x is a well-known function. It is known to be a decay function, whereas e to the x is a growth function. It is the opposite of. So e to the x does this, e to the negative x does this. Okay? It is a reflection across the y-axis. So now negative e to the negative x is now e to the x reflected across the y-axis and then reflected across the x-axis. Yes, sir.
So would the derivative of that be e to the negative x?
Derivative inside and yep. Mm-hmm. There you go.
Wow.
Pretty cool, huh? Yeah, pretty much. Which makes sense because e to the x has a derivative of e to the x, so It's not unreasonable. Okay, so let's try a couple more here. How about e to the negative 5x power? Negative 5. E to the negative 5x. I hope you're... Something like this, yeah. No, oh, come on, you guys.
Now you know that question.
No, the 70-point questions usually follow, I might throw in an x e to the negative 5x with a product rule. But that just means you're just adding, sure.
I know, that sounds really hard.
All right. I'll tell you what, you know what? We'll do a product rule when we do, let's do this next one, and then we'll do a product rule.
Okay.
Because I want to do something special with this one. Okay? Something special. Yes, sir. They were called, first student in my A3 class. Yeah. All right, so let's do e to the power of x squared. E to the power of x squared. 2x. And then what? E to the x squared. There we go. Right? Mm-hmm. Oh, thank you for saying that. Kiana just said that the chain rule is really easy now. You're right. Chain rule is a piece of cake. I hate the quotient rule. I'm not a huge fan of the product rule, but I love the chain rule.
I'm not a huge fan of calculus, but you know.
Understandable. Okay. All right, now let's say, I'm going to change this up a bit if you guys don't mind. Instead of making this y, I'm going to make it x of t. We're going to say that this is a position function. Instead of being e squared, we're going to make it t squared. Okay? And instead of making it dy dx, and it would be dx dt, but instead, what should I write here? Velocity, v of t, correct? The velocity, and we're going to change this to a t, and we're going to change this to a t. And now, let's say that we want to understand the acceleration of this object. We need the derivative of velocity. So a of t is going to be, now what are we going to deal with here? This is a product rule, because what we have is we have 2t times e to the t squared.
That's what we should have done on the quiz today.
Probably, if it's a, yeah. You've got to always be on the lookout for a, I can't tell you yet. I can't tell you yet. Because I'm filming. And there are people who are still going to take that. What I do is I typically change the questions up, but I usually don't change them up too terribly much. So I don't want to give anybody yeah. So.
That was going to be an advantage.
All right. Yeah, well, that's the interesting thing is actually you guys in B-Day are now alternating the lead. Right now you guys are ahead, but by this Friday they'll be ahead of you. So
They said they switched it up. All of our Fridays are B-Days now because we're missing school on Tuesday.
yeah, but only for 3 weeks.
Does that include this week?
Yeah, this week is a B. Next week is a B. The next 3 Fridays are B days. Yeah. Okay. All right. So bring it on. Let's do this for now. Okay. All right. So yeah, the derivative of, so we got to do the derivative of this, which is 2.
And then 2t.
Well, how does the product rule go?
Oh, the product rule.
Yeah.
To the t squared.
Times that, which is e to the t squared. All right.
And then
Plus
2t.
2t. Now hang on a second.
2t.
You don't have to do a whole lot of work here, do you?
No.
What is this? Doesn't that look like that? Right there? So wouldn't the derivative
Same thing.
of this thing be this?
Yeah. So it's 4t squared. Is it 4t
Right?
squared?
Times 2t e to the t squared. Right? Did you all follow what I just said? Did that make sense to you?
Now it makes sense.
Yeah.
So we can multiply.
Yes, we can multiply these. 2 times 2 is t times t is squared, t squared. That's right. So I'm going to change this up a little bit, and I'm going to make it 4t squared e to the t squared. There we go. There is the accelerate. That's acceleration.
We can't talk about
Yep.
the quiz at all, right?
Yeah. Now let's talk about it later. Yeah. So there you go. There's your product rule applied to an exponential function. And now If I asked you a question like, what is initial velocity? What is the initial velocity of the object?
Said it is 0.
Yeah, you would plug in 0 here, put a 0 here and a 0. It'd be 0 because 2 times 0 times whatever this is going to be 0. So initial velocity. So what's happening at time 0? What is this? This object is at rest. That's correct. At rest. It's all coming back. It's all coming full circle now, isn't it? But you know what? The body of knowledge is becoming more clear to you in your brain, which is what's important. You don't learn calculus in just a couple days. You don't learn pieces. It is a body of knowledge. It's like a giant model that you put together all year long. Okay? All right, so now, let's say that I said at time 1, what direction is it moving, and is it speeding up or slowing down? Okay, we'd have to identify what V of 1 is, and we'd have to identify what A of 1 is. AC, you got that? Okay.
Oh, I see what you did there.
Remember that note? Yeah, because it was like the third time you had done it on a quiz, and I was like, I need to end this now. He's not coming in to see me. I need to tell him now. This, yeah.
So that'd just be 2e for velocity?
Yes, velocity would be 2e. Note, e, 1 squared is 1. E to the first power is e. 2 times 1 is 2, so it's 2e. So velocity is simply 2e. And 2e is a better answer than 5.4365. Now on the AP exam, on the calculator section, and I'm eventually going to get you guys into using the calculator. I'm not going to leave you without a calculator for the rest of the year. Okay, you're eventually going to start using calculators. I just need you to be able to do calculus without a calculator for a little while. This is a better answer. This is approximately equal to 5.4365. Okay, that is truncated to 4 decimal places. Approximately equal to, but this is a better answer. Okay, now what about A of 1?
It'd be 6e.
Okay, well, this is going to definitely be e to the first power, right? So this is going to be 2e, okay, plus 4e. There you go, 4e. So yeah, you're right. It's going to be 6e. 6e, which is approximately equal to 6e, 16.3096. No, we could have done acceleration first. So it's speeding up which direction? To the right. It's speeding up to the right. Velocity is positive, and so it's moving to the right. Since velocity and acceleration have the same sign, it is... Oh, no. Remember, velocity is a vector, and a vector has both direction and magnitude. It's from Despicable Me. Yeah, direction and magnitude. The sign of velocity is its direction. Yeah. It's when Vector. I forget who Vector is talking to. Vector's the bad guy. Yeah, he's like, my name is Vector. His dad keeps calling him Victor, and he says, my name's not Victor anymore. My name is Vector. A vector in mathematics, a vector has both direction and magnitude, and I have both direction and magnitude. I forget how he does it, but it's really funny. Yeah. So anyway, if this was negative 2e, then it would be moving to the left, because it would be negative. Now, it's interesting you ask about positive and negative, because can anybody tell me when velocity will take on a negative value? When t is a negative number. There you go. Okay? Well, yeah, look at it. Okay, now here, first of all, will this piece ever be negative? No, e, if you did the graphs quiz or if you followed along with the exponential functions in your past math education, you will know that e is never negative. Negative e can be negative. E minus 5 can be negative, but not e to the x, okay? Or e, and it's certainly not e to any power is never going to be negative. But 2t, that can be negative. So if this can be negative and this is never negative, then there are times when velocity is negative. How about acceleration? When will acceleration be negative?
No.
Like it can't be. Oh yeah, when t is a negative number.
T squared. Acceleration is always positive. there's no minus sign, it's a plus sign. This will always be a positive number. This will always be a positive number unless it's 0. It can be positive or 0. If t equals 0, then we've got 0 times this is 0. But since this is a positive number and we're adding, acceleration is always positive on this, whatever this object is.
On this or period?
This particular unique situation.
Okay.
It is always, yes, oh, no, yeah. This particular unique situation, if that is the position of the object, then its acceleration is always positive.
So how would it stop?
What's that?
How would it stop?
How would it stop? It stops at one time. You may not know this, but the graph of e to the power of t squared looks kind of like this.
What are you trying to say, Mr. Ryan?
Oh, wait, I'm sorry, other way around. My mistake. So I was doing negative. No, I wasn't saying anything. But it looks kind of like this. At negative values of t, it looks like e to the positive t squared. So it does this, and on the right side it does the same thing. So it looks something like this. It stops and changes direction exactly once at time 0. Okay, looks a little bit like a parabola, and it is actually, I think it falls under the definition of a parabola. Maybe. I mean, it's smooth the whole way. It doesn't have any places where it's not differentiable. Yeah.
So is this one slowing down at 1?
At 1, no, it is speeding up. We have a positive velocity and a positive acceleration.
I thought. Okay.
Now at negative 1, it's still 6e, only this is negative 2e and approximately negative 5.43. So it is slowing down at time negative 1.
So when velocity and acceleration have different signs,
It's slowing down. Yep. Yeah. And one really cool thing about this function is that it is slowing down from negative infinity all the way up to 0.
So it's still speeding up.
No, well, it's slowing down until it gets to 0. At 0, it's at rest, and then from 0 to infinity, it's speeding up.
So I mean, it's slowing down, but it's getting to a higher rate. Like,
Slowing down means approaching a speed of 0. Slowing down means you're getting closer to... It is moving in a negative direction, but it is receiving positive direction force.
yeah, that's what I meant.
So it's slowing down. Yeah. Okay, so that's that. Now let's talk about natural log problems. Let's go to question number 15. This is good stuff. Let's say y is equal to the natural log of x squared. What is dy dx? This is cool stuff. Yes, start with 2x, right? Why? What are you applying here? The chain rule, yes. All right, so we're applying the chain rule. So we've got 2x times the derivative of the outside, which is, no, this is natural log. 1 over x, but instead of 1 over x, and please be careful. See, this is something that's going to mess. It's x squared. You got to put the inside function right here. Don't put 1 over x. You got to put the inside function there.
So like,
Say that again.
It's like the quiz.
Yeah, you have to every time you've done the chain rule in a quiz, if you have had an inside function, you have to put that inside function in the answer.
so
Yeah.
So if the x, like it probably was like 3x or something like that, you would keep that when you do.
Yes.
Okay. Cool.
Yeah. So we got 2x times 1 over x. What does that equal to? That's 2x over x squared, right? So it's actually 2 over x. We cancel an x. Cancel that x, cancel one of these x, and we have 2 over x. Yes, sir.
Never mind. It's related to the quiz.
Okay. All right. I'm going to do another one now. We're going to do natural log of x to the 3rd power. Okay, 3x squared times 1 over x cubed, which is 3x squared over x cubed, 3 over x. Want to prove it? I do. You ready? All right, first you tell me what the pattern is.
3 over whatever the
It's the power, that's right. It is the power of the x. It's the power of the x over x. Okay? Now, I'm going to show this to you in two ways. Watch this. You ready? Everybody be ready. Look, check this out. Did you know that this is equal to the natural log, or excuse me, it's equal to 3 times the natural log of x? There is a rule of logarithms that says that you can take the exponent on your argument and move it to the, it turns it into multiplication. Logarithms turn exponents into multiplication, multiplication into addition.
So cool.
Yep, they turn roots into division. They turn division into subtraction. It's amazing. That's why logarithms are so awesome.
So is that why it's called root?
Um,
I get it. No.
That's a good question. I don't know. I don't want to answer that yet. It could be. But here's the thing. Logarithms are an amazing thing. I may have said this before, but logarithms, the development of logarithms actually pretty much set off the Industrial Revolution and eventually yeah.
No, how?
It reduced the amount of time it took to do complex calculations because it turned exponents into multiplication. It takes a long time without a calculator, without a computer. You know, back in the 1600s, it took a long time to do exponents, especially if you were doing powers instead not to the third power, but you were doing it to the e power or to the, well, that doesn't make sense, but to the 2.72256 power, the 2 point, or worse yet, what if you wanted to know what the exponent was and the exponent was 17.936? Took a long time, probably a lot of trial and error. They did have calculators, they had mechanical calculators, still took a long time. Logarithms, yeah, you're glad that John Napier, I think his name was, or something like that, he figured it out. And then he wasn't even a professor of mathematics, but man, they went nuts over it. Good stuff. Yeah, logarithms changed the world. If they hadn't come out with, if he hadn't developed logarithms, then it's possible we wouldn't even have cell phones these days. We might even be in the middle of the Industrial Revolution right now. So, yeah. It really, logarithms really did change. This is all theoretical, obviously. You can't, or hypothetical, excuse me. You can't.
Slavery would have ended, or would it last longer?
That's a good question. No, that is a good question. That is a very... Right, it's a good... I don't know, but it is a good hypothetical question because the end of slavery and the civil rights movement in the 1960s had to be a direct result of the development of moral ideas. And moral ideas generally don't develop in a society until after economic development. We have to be comfortable. Listen, we have to be comfortable enough in our life to think about morality. If we're dawn till dusk working our butts off, cutting and digging and stuff, we don't have time to think about whether this is right or wrong. We just want to put food on the table. Yeah. Okay. Yeah. Okay. So, look. So if the rule of logarithms says that this is the equivalent of 3 natural log of x, now we don't have to worry about the 3. We're just going to multiply by 3, right? It's going to be 3 times whatever the derivative of natural log of x is. What's 1 over x? Isn't that awesome? Which is 3 over x. Isn't that easy? Yeah. No. That is how you can do it if you want to. Now, no. Actually, honestly, I think that it's possible for a person to get tripped up if they're not careful. Okay, but here, watch this.
Try to give us a chance to write.
Well, I'm going to do it again. Here's what I'm going to do. Here's what you want to write. Look at this. Let's say that we have natural log of x to the k power. Natural log of x to the k power. Okay? Well, we're going to do the derivative of the inside, which is k times x to the power of k minus 1. Right, but I'm doing a general rule for any value of k.
Wait, why is it minus 1?
Because we always subtract 1 from the exponent. We don't know what k is going to be equal. We know it's a constant, but we don't have a value for it. So to represent the exponent, we have to do k minus 1. Don't we always subtract 1 from the exponent in the power rule?
Oh, okay.
Okay. All right, times 1 over x to the k power. And now this is going to become k x to the k minus 1 power over x to the k power. right? And now, can we agree that x to the k power is the same thing as x to the k plus 1 minus 1? Okay, so then that would be x to the k minus 1 plus 1. No, I did associative property. I just moved the negative 1 over here, the plus 1 over here, and then put parentheses around the k minus 1. I'm trying to show you that this and this is going to be equal to x to the k minus 1 times x to the 1. I'm just doing a little bit of algebra here. And now look, this can cancel with this. And what do we have left? K over x. K over x. So whatever the power is, the derivative is going to be that number over x. Okay? All right, let's do another one. But not this one. We're going to do it a little bit different. Now we're going to do the natural log of 2x. The natural log of 2x. How should we start?
Get the derivative of the inside.
Which is? 2 times?
2 times and then
1 over 2x. Derivative of the outside, inside unchanged, which is 2 over 2x, which is 1 over x.
Oh my gosh, how does that work?
It's logarithms, man. They are awesome. If this is not enough to convince you that logarithms are about one of the greatest mathematical contraptions, then I don't know what is. Logarithms are awesome. Logarithms answer the question, how long until? How long will it be until? How long will it be until there are 500 million people in the United States? Well, it's a logarithm. Yes, sir. Can I do it later? But let me give you the basis. The basic idea is, well, I'll do it now. Look, let's say growth in the United States, let's say that we have, 350 billion people, or a million people, 350 million people, and to the power of, let's say our growth rate is like 0.04 t, and t is in years, so let's say it's 4% per year. So that's probably high, but I'm just throwing something out there, is equal to something. So if you say in 5 years, how many people will there be? 0.04 times 5 is 0.2, so multiply 350 times e to the 0.2 power, and that'll tell you how many people there are. That's exponential growth. Well, if we want to know, if we want to answer for t, we want to know how long it will be until there are 500 million. Well, we would divide by 350 here, divide by 350 here, and now how are we going to undo this? We are going to apply the inverse of e, which is, the inverse of e is the natural log. Natural log and e are inverses. So, the natural log of e to the x equals x. And e to the power of the natural log of x squared equals x squared. They cancel each other out. E and natural log are inverses. They cancel each other out. So now the question here becomes, it becomes 0.04 t is equal to the natural log, excuse me, sorry, natural log of 500 over 350. So you can see that natural logs answer the question of how long until. Isn't that neat? And it's not just natural logs, it's all logarithms. Log base 2, log base 10, log base 7, whatever. Okay?
People have jobs that sit around and do that all day?
And they get paid lots and lots of money.
So why don't you do that, Mr.
Um,
Don't incriminate yourself.
Usually high stress. You have to find the job. There's people who compete for those jobs. I'm not sure if I would be happy in a job like that. But I do encourage people. I believe that people who are masters of exponential and logarithmic functions can make more money than anybody else. That's what I believe. Okay. All right. So now let's try. We're going to change this up a little bit. Natural log of 3x.
It's still going to be 1x, which is...
1 over 3x equals 3 over 3x equals 1 over x.
How can you make this hard on the quiz then?
Oh. No. I would probably give you 1 or 2 of these. Watch. How about natural log of x squared minus 5? This now is suddenly different.
So it would be like
2x, 1 over x squared minus 5. Yeah. And now it becomes 2x over x squared minus 5. You can't cancel anything.
That's so easy. I like
It is. It's really easy.
So this is how we get our grades.
Yes! I like the sound of that.
What about the challenge question?
Wait.
Oh, sorry. X minus 5, x squared minus 5 equals 2x over x squared minus 5. There we go.
You know what Mr. Young used to do to give us extra credit?
What's that?
He used to ask us random questions.
Like movies,
Like-
trivia.
Oh, that's
Like-
cool.
Yeah, you should do that. Like,
I could do something like that, but I feel like some people would be at an advantage over other people.
I mean, not really. He asked us, like, what's his favorite Simpsons character?
Oh, I see. Yeah, there was a professor, my economics professor, who's one of my favorite professors in my undergrad. On one of his tests, he said, it was extra credit, he said, what is the mascot for Palm Beach Atlantic University? That was our university, Palm Beach Atlantic. I didn't know. Sailfish Jack.
That's what it was?
Yeah. Sailfish. I knew it was a sailfish, but I didn't know his name was Jack.
Like what was
mean-
like the word, like the challenge songs, like the like how.
Oh, well, I mean, remember that one that I just did with the motion? I could do something like that.
Oh yeah.
That's right. What kind of bug is that in that window?
That's a spider.
That's a spider?
Yeah, it's a spider. Yeah. I could ask for the equational line tangent to the graph of, you know.
I think it's that. I'll ask them.
Yeah. Okay, so are we okay then with derivatives of natural log? Derivatives of natural log, or logarithmic functions, derivatives of exponential functions. I think they're pretty easy. Once you know the chain rule, once you know the product rule, once you know the product rule, or the quotient rule, these questions are very easy. Okay? So we're now going to turn our attention to chapter 4 and section 4.1. 4.1 is extreme values of functions. Okay? Here's what I want to start with. Now, extreme values of functions, what we're talking about here is sometimes they are called extrema. Okay? That is a plural term. Its singular is extremum. That is one extrema. Okay? Or one extremum. Okay? These are often understood to be maximums, and minimums. So what we're talking about here is identifying the maximum points and the minimum points on a function. Now there's two kinds of maximums and two kinds of minimums. Okay? There are absolute maximums. There are absolute minimums. And then they're what are referred to as relative or local maximums and relative or local minimums. Okay, so you've got absolute maximums and absolute minimums, local maximums and local minimums. They all fall under the general term extrema or extremum, or an extreme point. Okay, an extreme high point or an extreme low point. I'm going to draw a graph over here while you write that down. Okay, here's the graph. We're going to draw, let's see, it's going to start here. It's going to be on a closed interval, and it's going to look like this. Let's say it goes like this. Well, you know, let's stop here. There we go. Right here. Okay, this is going to be an x value of b, and this is going to be an x value of a. So we have the interval, the closed interval from a to b. At this point right here, we are going to call that internal point C1. We're going to call this internal point C2. We're going to call this internal point C3. And this is going to be internal point C4. Okay? Is this all acceptable to you? Okay, so here's what we are looking at. Can anybody, just looking at this graph, identify the absolute? Well, actually, let me talk about absolute and relative first, and then I'll ask you to identify. And on an interval, you can really only have one absolute maximum, and you can really only have one absolute minimum. And I'm going to explain there's three ways that you can identify an absolute maximum. 3 ways. And it's the same 3 ways to identify an absolute minimum. 3 ways. Okay? But there's only 2 ways to identify a relative maximum or a relative minimum. 2 ways. Okay? I'm being very general here, but the idea is that there's 2 things that indicate a relative and 3 things that indicate an absolute maximum or minimum. So an absolute maximum and an absolute minimum, that is the highest point on an interval. And an absolute minimum is the lowest point on an interval. Okay? So there's only one of these and there's only one of these on an interval. Well, okay, actually, let me take that back. Sorry. There actually can be an infinite number of absolute maximums. There can be an infinite number of points that are the absolute maximum. For example, if I have a parabola and my interval is from here to here, both of these points are at the same height, right? There is still only one maximum value. It just happens to occur at more than one point. Does that make sense? That's what I mean by there can only be one absolute maximum and one absolute minimum. Only one output value that is the absolute maximum and only one output value that is the absolute minimum. Okay? So, a relative maximum and a relative minimum, those are simply just a change in direction. Okay? They are places where the graph turns around. But they might not necessarily be the lowest point and they might not necessarily be the highest point. They might be the highest point. A relative maximum can be an absolute maximum also. But there are lots of places where you can have a relative maximum and not an absolute maximum. Now, given that, I know it's a little confusing, but let's look at the graph now and see if we can decipher what I just said. Does anybody see the absolute maximum on this graph? At C1? I agree, it's at C1. It is the absolute highest point, the highest y value on this graph. Okay? That is the absolute maximum. Is there a change in direction at that point? There is, meaning it is also a relative maximum. Relative means in the vicinity of that point, it is the highest point. In the neighborhood. In the limited neighborhood of that point, it's the highest point. That's what relative means. Local. A local maximum. Does anybody see a local maximum that is not an absolute maximum? C3. C3. Sure enough, there it is. It's not the highest point, but it is a high point locally. Okay, so C3 is a relative maximum. Does anybody see a relative minimum? C2. C2, yeah, it's not the lowest point, but it is a low point locally. How about the absolute minimum? C4. C4, there it is. What's interesting about C4 there? It is the absolute minimum, but there's something else interesting about it. It's actually, I would call it, look, it could be a cusp. I think it's a corner, but yeah, but you get it. It is definitely not what? It's not a curve, it's not smooth, it's not differentiable. That's exactly right. Which means it is continuous though. Sorry, it's not a jump, it's not a hole or anything. Which means that we can have absolute minimum points at a place where the function is not differentiable. Okay? So, I'm going to change this up just a little bit, and then I'm going to ask you guys most of those questions again.
C4 would be considered to be a relative, right?
No, it would be a relative minimum. Yeah. Yep, it would be a relative minimum.
So was B absolute but not relative?
B was, well, it's about to be. All right, watch this now. Watch this. Now, I've changed the graph a little bit. Guys, settle down. I've changed the graph a little bit. Is C1 still the absolute maximum? No. Where is the absolute maximum? It's at B, which is one of the, what do we call those? The endpoints. The absolute maximum is at one of the endpoints, but it is not a relative maximum. Okay, correct. That's exactly right. It's not considered to be a relative maximum. Okay? And that's what these ways are that I'm about to explain to you. I'm going to erase this, and I'm going to make a list here that you're going to want to write down. Here's the idea. Correct. Here's how, let's say how to find a minimum or a maximum, okay? So let's say we all gather together, we've had a minimum that ran away and it's lost, and we've got a maximum that ran away and it's lost, and all the neighbors come together, and we all get, you get all your friends and neighbors together, and you say, okay, listen, we got to look for the minimum, we got to look for the maximum. I'm going to give you guys some instructions on how to find the minimum and maximum, and once I give you those instructions, you guys run out, we'll find them, okay? All right, there's 3 basic ways to find a minimum or a maximum. The first one is this one right here. When this one was the absolute maximum, what do we know about this in terms of its derivative? What do we know about that point in terms of its derivative?
I want to say it's 0.
It is 0.
Okay.
Why? Because it has a slope of 0. This has a slope of 0. It has a horizontal tangent line. A tangent line with a slope of 0. Which means, and does that, the relative minimums and maximums, except for this one here, do they also meet that criteria? They do. Every single one of these except for this one, these ones that are smooth, they all have a slope of 0. Which means that the first and most of the time best way to find the minimum or a maximum of a function is to find where, you say it, where the derivative equals 0. So step 1 is just find where dy dx equals 0. And solve for x. Find where dy dx equals 0, and then solve for x.
That's not stuff we just did.
What's that? Yes. Yeah. Very similar. Yep. Remember we were having the conversation about when can the velocity equal 0 here and that kind of stuff? Yes. Very same thing. Yes, ma'am.
So you know how we used to look at the position time graphs and then we would find the derivative, so we would have the derivative graph. Are we ever going to be given a derivative graph and it asks what is the minimum and maximum of the original?
More times than you will care to do, yes.
Okay.
That is probably one of the most popular types of questions on the AP exam. They give you the graph of the derivative and they expect you to be able to identify where the minimums and maximums are. But I'm going to show you, it's so easy. It's very easy, especially with either a sign chart or with the graph itself. You can very simply identify where minimums and maximums are. When we get to section 4.3 and we learn about what's called the first derivative test, it'll be very easy to identify where the minimums and maximums are. You'll get very good at it. There's also what's called the second derivative test, which I love. I'm a huge fan of the second derivative test. I like it better than the first derivative test. It's actually easier in my opinion. Well, depending on the function. All right, so the second way that you're going to find minimums and maximums is you are going to look for where dy dx does not exist. Okay. Remember that the derivative is a limit, right? And so wherever the derivative does not exist, we call this, what do we call this? Not differentiable, right? So anywhere where the function is not differentiable, you're going to look for minimums and maximums there, yes.
So if it's 1 over 0, limit?
Yes, that would be a vertical tangent line. Yep, it could.
1 over 0 is,
Yep,
that's a vertical tangent.
that's a vertical tangent line.
So that means that doesn't...
If the derivative equals 1 over 0.
And what does that mean?
That means, that could be it could also be a cusp, because that winds up happening. The limit equal, it doesn't exist. The limit itself is a vertical asymptote in implying a vertical tangent line. Okay. All right, so now, and then the third place you're going to look is at the endpoints. You are always going to test, unless there are no endpoints, which happens sometimes, or unless you know logically that it doesn't make sense for the endpoints to have the maximum or minimum. Okay? But you better know logically, not that you don't have to check it. So, for example, let's say you're given some function, some situation where you're trying to find the maximum volume of an object, and one of your endpoints is, let's say it's a sphere or a cone or some weird shaped cylinder. One of your dimensions is radius. Now, if the radius of the object is 0, is it even going to have a volume at all? No, with a radius of 0, whatever it is, whatever three-dimensional object is with a radius of 0 will have no, so you know that that is not going to be the maximum. So you're not going to even check, you may not even check the endpoint. Now, if you're being asked about the minimum, yes, then 0. Okay? We're usually not trying to minimize volume, though. We're usually trying to maximize. So we're going to check the endpoints. So you are always, so anytime you're given a problem where you have to identify maximum or minimum, what you're going to do is you're going to set the derivative equal to 0, solve for x, find any places where it's not differentiable. That's any jumps in the derivative, places where it's not continuous. Remember that a discontinuity means that it's not differentiable, right? And anywhere that it has a vertical tangent line, okay? And then you're also going to check the endpoints. And in this particular case, the right endpoint is the absolute maximum. We okay so far?
Wait,
okay. Yeah.
We're just given the equation. How are we supposed to check the endpoints?
You'll be told here's the equation on the interval from 1 to 7. Yes. And then you'll check 1, you'll check 7. You'll find now if the derivative equals 0 at 17, you're not going to check 17 because it's not on the interval. That's correct. You are only going to check these values that are I should say solve for x for interior points, I should say, for interior points. Same thing for where it doesn't exist, for interior points. Okay, so if your derivative equals 0 at a point that is outside of your interval, don't worry about it. Just leave it alone. Don't even bother. Okay. All right, and by the way, this whole thing is the same idea. Remember when the questions where I've asked you to identify maximum acceleration and minimum velocity? That's this. Only I gave you problems where you didn't have to do 2 and 3. I had only taught you how to do number 1. Does this ring a bell at all for anybody? A little bit? Okay. All right. What I want to do now is I want to draw your attention up to the overhead projector here. And this is on page 188 in your textbook in the left column, and I want to talk about these graphs. This is the graph of x squared. And what I'm about to tell you about is what is called, we're talking about how to find extreme values of a function, but what I'm now going to explain to you is called the extreme value theorem. It is one of the 5 major theorems in AP Calculus. Okay? And I don't believe it is as terrifying as the intermediate value theorem, but I also don't think it's as cool as the intermediate value theorem. That's my opinion. So let's say we have this function, x squared. This is the graph. And let's say its domain is from negative infinity to positive infinity. So tell me about the interval.
It's infinite.
Yeah, we don't have like a hardcore, a hard finite left or right endpoints. So there are no endpoints here, is basically what we're saying. No endpoints. What is the absolute minimum of this function?
0.
Yeah, it's 0. At x equals 0, right? It's at the point 0, 0. We okay with that? All right, what is the absolute maximum?
Oh, it's
Good. That's the best answer you can come up with, but really?
What?
No, I'm saying, but really, there is no maximum.
I thought you said like,
Yeah,
really?
really?
Oh, no. I'm saying, but in reality, there is no maximum. If infinity is your maximum, then there is no, because infinity is not finite. Okay? So, this graph right here, without endpoints, just a parabola, has no maximum, has no absolute maximum. It does have an absolute minimum. Okay? If we were to take a situation like a cubic function that does this, if you didn't give it endpoints, would it have an absolute minimum or an absolute maximum? No, not at all, because the left end goes to negative infinity and the right end goes to positive infinity. Okay? All right. Let's move on now to this next graph. That was me swooshing up. Okay. Now we have x squared, but now we have a closed interval from 0 to 2. Do we have an absolute minimum?
Yes.
What is it?
0.
0. Okay. How about an absolute maximum on the interval?
Yes. 2.
Yeah, what is it? It's 2. It's at x equals 2, the absolute maximum is 4. Right?
Yes.
Okay, we're okay with this?
Yes.
All right, so now that we have created a hard and fast interval, we can have an absolute minimum and an absolute maximum.
I know somebody's watching you this run.
Somebody is. Just not right now. Somebody is watching you in the future.
Yeah, when I'm famous in 20 years, they're going to look back at this video and be like, wow.
And they're going to learn calculus. Yeah. Okay. Now, how did the interval get changed here? That's correct. This is now an open interval on the left end. This is now not including 0, but it is including 2. So what is the absolute maximum?
2.
It is, well, at x equals 2, the absolute maximum is 4, right?
Oh.
Because it's
Yeah. Does it have an absolute minimum?
No. Because
No,
you
it does
can't
not.
have one on because it's not differentiable.
Well, it is. You're right. It's not differentiable at the end, but isn't places where it's not differentiable, don't they qualify for possible minimums and maximums?
Yes.
Okay. But here's the question. If someone said, yes, there is an absolute minimum, I would give them $1 million when they finished telling me what that absolute minimum is.
You have to keep saying .00000.
And I would die before they died, probably. And they would die before they finished. See what I mean? So, because the next number next to 0, it's real, it's there, we just don't know what it is. We can't say it.
Well,
Okay? So, what's that?
when we say the same thing as infinity, because it's going to.
It is infinite. That's correct. It's infinite. It is not infinity itself, but it does have an infinite number of zeros between the point and the 1.
Well, couldn't they say,
Okay.
like, what is it called? What is like a really big number, but you simplify it? So it's like 2 to the 10th power?
Yeah, but you'd have to do to the infinity power, and now it's suddenly infinite. So the idea here is that if you do not have a closed endpoint, then you can't. If the minimum would be at the endpoint, then you have no absolute minimum. Now, I do want to show you a situation. Let's say that we have this. Let's say that the endpoint over here is open and the endpoint over here is closed. Do we have an absolute maximum?
No. Wait. Yes.
There.
Yes.
Do we have an absolute minimum? Yeah, down here. So just because it's one of the endpoints isn't closed doesn't mean we don't have an absolute maximum and absolute minimum. Did y'all recognize the difference between that point and this point? Okay. So you have to consider where is the endpoint. Okay. All right. Let's do one more, and then we will do the extreme value theorem. This last one here is the interval from 0 to 2, open interval on both ends. Right, it is not defined at x equals 2. It is not defined at x equals 0. What's the absolute maximum? There is not one. What's the absolute minimum? There is not one. That's correct. This function on that interval has no absolute maximum and no absolute minimum at all. Okay, so this brings us to what is called the extreme value theorem. You're going to want to write this down. And actually, yeah, let me put it up on the board. I think I have time to put it up on the board. So the extreme value theorem, this is what it says. It says, oh, you know what? Hang on, I'm going to put it up on the screen because I am running out of time. Where is it? Oh, it's right here. The extreme value theorem. Look up here. This is what it says. The extreme value theorem is on page 188. It says, if a function, if f is continuous on a closed interval from a to b, then, now notice, I don't know if you noticed, there's two conditions here. What are the two conditions? One, that it's continuous. The second is that it's on a closed interval. See, you can have a closed interval. Watch this. Okay, this is A, this is B. Do you agree that this is a closed interval? Yes. Does this have an absolute maximum? No, this would be the absolute maximum, but it's open. Does it have an absolute minimum? No, it would, except that open. So even though it's a closed interval, it does not have a maximum and it does not have a minimum. Why? Because it's not. No, it's defined. Oh, it's not defined at that point, but that's not the main. That's part of it. But really, the key is it's not continuous because the function is not continuous on the interval from a to b. A to b is not guaranteed to have an absolute maximum and an absolute minimum. So, if f is continuous on the closed interval from a to b, then f has both a maximum value and a minimum value on the interval. Guaranteed. It absolutely will. Now let me ask you another question. Let's say that it is not continuous and not on a closed interval. So this is A on the interval from A to B, but it's an open interval. And, oops, that's B. And it's not continuous. Does that mean it absolutely does not have a minimum or maximum? No, we can't conclude that. We just can't use the extreme value theorem to guarantee it. Remember we went through that with the intermediate value theorem? The intermediate value theorem doesn't guarantee something doesn't exist. It guarantees that something does exist. The extreme value theorem does not guarantee that you don't have. It just guarantees that you do have. So even if it is not continuous, even if it is not on a closed interval, it can still have an absolute maximum and an absolute minimum. Okay? So that's the extreme value theorem. What I want to do now is I want to do a textbook problem so that you can get a feel for how this works. Okay? I'm going to go to section 4.1, and in the homework, I'm going to put it up there. I believe it's question number 11, and this is what question 11 says. There it is. Question 11 says, in exercises 11 to 18, other way. In exercises 11 to 18, use analytic methods to find the extreme values of the function on the interval and where they occur. And it says f of x is equal to 1 over x plus natural log of x. F of x equals 1 over x plus natural log of x. So what's the, and it says on the interval from 0.5 to 4. First thing I need is the derivative. F prime of x is equal to, I don't know if you remember this, negative 1 over x squared plus 1 over x. I'm going to set the derivative equal to 0. And now I'm going to, algebraically, I'm going to move this over to this side. So now I have 1 over x is equal to 1 over x squared. Now, we cannot include 0 because the denominator cannot equal 0. But is there any value that will make this true? Negative 1? I don't think negative 1 will make this true. Just 1. Positive 1. Is positive 1 on this interval? Yes. So one possible solution is x equals 1. In fact, that's the only solution for a slope of 0. So now I want to identify, do I have any places where it's not differentiable? 0, but that's not on the interval. Right? Okay, so here's what I want to do. I have 3 what are called candidates. I have 3 candidates for minimum and maximum. I have a critical number. This is called a critical point. I have a critical point, and I have 2 endpoints. And I'm going to make a table. X equals 0.5, 1, and 4. And this is going to be my f of x values. And now I am going to plug each one of these values into this. And because we don't have much time, I'm just going to show you what I got for each of these answers. This, if I plug 0.5 in, you will get, oh, I'm on the wrong page here. You get 1.3068, 1.3068. I had to use a calculator. When you plug 1 in, you'll get 1. And when you plug 4 in, you'll get 1.6362. This is question number 11 in the textbook. Now, the maximum is at 4, the absolute maximum is at 4, and where's the absolute minimum? At 1, and the absolute minimum is at 1, and you are done. Okay. I just plugged these numbers into this.
So you just put the endpoints in
You have to plug in the endpoints and the critical points, called a critical point or a critical number or a critical value. Okay? And that's it.
So we don't have this class until Monday?
Next Monday, that's correct.
Mr. Ryan, look at that leaf in the window.
Yeah.
Doesn't it look like Batman? The Batman song?
It does actually look like Batman.